Okay, so before getting into looking at any examples, uh, let me talk a little bit about how I did with the horizontal architecture last time. I'm going to talk a little bit like that for the vertical. So with the horizontal, let me actually pull that up. With the horizontal here, oh, come on, there we go. So with the horizontal, you essentially have a whole bunch of little switches everywhere that allow you to control exactly what's going on in the circuit. And you have to basically, in your instruction, you have to set each of those manually. You have to say, okay, I want the two function things to be exactly this. I want the shifter function to be exactly this. I want the AMUX input to be exactly this, right? You have to set every single one of those things manually in the instruction. That's a lot of work. And also, I mean, even if you just look at this right here, just the shifter portion not used, every single instruction with a 3 here is invalid. That ends up being a fourth of all instructions that are just not valid, right? Like essentially, you could think of each instruction as just some random 32-bit string of ones and zeros, right? It's just a single 32-bit number, and if you add up all these bits here, you do get 32. And so a fourth of those are just invalid, and that's sort of weird. And you can also do like dumb things where you go from the MBR, pass it through the AMUX, through the ALU, through the shifter without doing anything, and then storing it right back into the MBR. That doesn't really make any sense. That doesn't do anything useful. And as a result, it's never really all that useful to give the user this much control over the CPU. It's generally way easier to just essentially give you a set of things that you can do and an easier way to represent those. And that's exactly what the vertical architecture does. Is instead of having to specify exactly how the CPU needs to pass the data around, the CPU defines a predefined set of things that you're allowed to do, and then you just do those. And the benefit of this is that now the instructions here, if you notice, op is 4 bits, R1 is 4 bits, and R2 is 4 bits. Your instructions are now only 12 bits, as opposed to 32 bits. Which means you can fit roughly 3 vertical instructions per horizontal instruction. And, there's maybe some argument that because these instructions are more specific, they can actually be run faster, or at least some of them can. But I won't get into that. But the idea here is you can save a lot of space without really sacrificing anything. And yes, it might take more cycles, but the purpose here is making sure that whoever's using the CPU can't just completely ruin it by doing something undefined or just pointless. And so really what ends up happening is that all of the work that you have been doing so far in filling all of these things out is now put into a circuit, and it's called the op decode. And so it'll get this op here, and based off of what operation it is, it figures out what all of these need to be, except for A, B, and C, which are specified by R1 and R2, and as well as the address that's also specified by R1 and R2 in different circumstances. But yeah, all of these bits here are figured out by op. Using this op decode, and it makes sense. This is a slightly more complicated way to make a CPU, but it ends up being a lot easier to use. And really, when you're having to do anything with the vertical architecture, this thing doesn't matter. You obviously need to know the register names and everything, but the only thing you really need to look at is this table. This table tells you everything that you might possibly want to do. It doesn't matter how the actual CPU is structured. All that matters is how the instructions are meant to be structured and how you have to format them so that the CPU understands what's going on. And so we can start to take a look at things. The one thing, though, that's perhaps worse about the vertical architecture is that you have a limited set of instructions. You can't just do anything that the CPU could possibly do. You're limited to a set of things. And we'll see how that comes into play. So, any questions on any of that so far? All right. So, I'll look at just a really simple example to start with. Let's just do A equals a plus b. So now what you want to do is you essentially want to look at this, and you want to look at these instructions here and see if any of the instructions here matches the pattern of the instruction that you're trying to do. So here we have some register x equals another register x plus another register y. And here I'm just using x, and y as variables because you can see here that op9 has exactly that form, x equals x plus y. And that's op number 9. So in order to convert this into a vertical instruction, I'm going to have my op, I'm going to have my R1 and my R2. And so my op is going to be 9 because I want to do that x equals x plus y. Then x, whatever x is, which in this case is a, is what I'm going to put as R1. So here I'm just going to put a for now, but I'll translate it later. And then for R2, that's going to be y, so y is b, and so I'm going to put b in R2. But really, we're not going to put letters here, although you could argue that this is also the hexadecimal value of the registers. The hexadecimal value of a, or a is the hexadecimal value of 10, b is 11, c is 12. So you can see that those correspond exactly here. But really, you would want to put the numbers here, unless you're specifically asked to put it in hex or something. So in this case, R1 here would be 10 because 10 is registered, or A is register 10, and we would put 11 here. And that's the instruction. That's all we have to do, right? 9 says take this, add this to it, and the CPU just knows how to do that from there. A lot easier than having to figure out how the data needs to flow and all of that. It becomes entirely irrelevant because of how everything is defined. Any questions on this little example here? All right. Now let's do something a little bit more complicated. So as you will definitely see, you usually can't just do something in a single instruction. So the instructions are so basic here that if we do anything slightly more complicated than what I just had written, it suddenly becomes impossible to actually do that in a single instruction. So now if I have a equals b plus c, and you look over here at all of the patterns, you'll notice that there's nothing that actually matches this pattern. There's x equals x plus y, but that doesn't fit this pattern because x would have to be a and x would have to be b at the same time, which isn't possible, right? So what we would really want is something that's like x equals y plus z, but none of these match that instruction. So you're actually going to have to break it down into multiple steps and multiple instructions. So the first step here that you want to do is you want to take your instruction, and I didn't really do it for that first one because it was already an instruction that could be executed, but you want to translate whatever you're trying to do into a set of instructions or a sequence of instructions that would implement that, but where every single instruction is one of these operations. So here, what I might do is I might say start off with just a equals b, right? So I'll take the value of b and move it into a, and then I'll add c onto that. So a equals a plus c. And now you'll notice here that this first instruction, a equals b, that corresponds to op number 11. And this next instruction is just op9 again. And so if we do op11 with this configuration and op9 with this configuration, we're going to do this. And that's the goal. So now we can go ahead and translate all of these into the op R1 and R2, the actual instructions. So here we've already figured out that it's op11 followed by op9. R1 here, we can see that, well, for op11, it's x equals y, right? So we want to do a equals b. So that means x is a, y is b. And then it also states, R1 is what x is, and R2 is what y is. So R1 is a, and R2 is b. But again, we'll write out the numbers here. So that's 11 and 10. So this operation here says move the value of b into register A. Then we have number 9, which is x equals x plus y. R1 is x, R2 is y, And we already know that x is a, because we want to do a equals a plus c. And then y is going to be c this time. So now we have R1 as a, which is 10, and R2 is c, which is 12. And so this is our program, and that's it. Don't have to look at any sort of flow of data. You just have to make sure you can break down the instruction into a whole bunch of different ones that can be executed atomically. And the same technically goes for the horizontal. You may have to convert a single sort of program into multiple instructions in the horizontal. That is definitely not something that's off the table. Any questions on any of this so far? All right. So next, let's look at the way that doing conditional branching works. So in the horizontal, or let's say I have this instruction here: a equals a plus b. Just doing something simple. If n go to, I don't know, 32. So what this means here, what this instruction means, is do this operation here, a equals a plus b. If the result of this operation here, doing a plus b, is negative, if that result ends up being negative, then go to 32. So what we want to do here is essentially detect whether a plus b, the result of a plus b, was a negative number. And so we want to use this if n go to x operation. So what we might do, a equals a plus b. But on the horizontal, what happens is you can do this a equals a plus b, figure out that it's negative, right? This n output here will be a 1, and then this will happen. So then it'll say, oh, n was a 1, so I'm going to go to 32 for the next instruction. The problem is that in the vertical architecture, the n and z flags are not just set every single cycle. You have to set them manually using an instruction. And that corresponds to instruction number 5 here. And this instruction, the syntax ALU equals x and z, all that means is pass some data into the ALU, check if it's n and z, and set those set the flags there on the CPU. And essentially, there's just 2 D latches somewhere, right here. There's just 2 D latches in there that'll store n and z whenever this line turns into a 1. It'll just copy store whatever those are, and then it can be used later to do the actual jumping. So the first thing that we want to do here is obviously the a equals a plus b. So now I'm breaking this down into a sequence of instructions that can actually be executed on the vertical architecture. So a equals a plus b, that is again operation number 9. Then we want to do ALU equals a and z. So this is going to take the value of a, right, which was the result of this operation. I'm going to take the value of a, put it into the ALU, and then set the n and z flags accordingly. And that's operation number 5. And then finally, we can do the if n go to 32. So that's operation number 7. We'd have if n go to 32, which is, number 7. Okay, so now we can go ahead and write out all these instructions. So we have op R1 and R2. So we have operation number 9, 5, and 7. For number 9, we're doing x equals x plus y. R1 is x, R2 is y, and we're trying to do a equals a plus b. So y is b, x is a, and so in R1 I'll put 10 for register A, and in R2 I'll put 11 for register B. Then for op number 5, if you look here, we put whatever we want to pass into the ALU, which in this case is A, in R2 specifically. So here I'm going to put A in R2. A is register number 10, so we put it here. And I'll just say that I don't really care what R1 is because it's going to get ignored anyways. So then for number 7, here it says if n go to x. So here our x is 32. Put x in R1 and R2 simultaneously, or something like that. What this means here is that, well, notice here that the address is 8 bits. It's supposed to be an 8-bit number. And you can even see this here, that R1 and R2, if you follow them along, they both sort of branch in and then combine together. And that's because when you're doing operations 6, 7, or 8, here you can see they all have that same sort of syntax for the register assignment. Instead of treating R1 and R2 as two separate 4-bit values, you want to treat it as one single 8-bit value, so that you can actually pass in a full address here. And so really, the value of 32 is going to be put into both of these registers simultaneously. 32 isn't a 4-bit number, right? 32 is this, if I'm not mistaken. No, one more. 32 is that, right? It obviously doesn't fit into 4 bits, but it does fit into 8 bits. And so that's what that syntax means. It means treat R1 and R2 as a single 8-bit number. Because remember, these instructions are just single 12-bit numbers. Every single 12-bit number here just represents a different instruction. And so, and all we're doing here is we're saying, okay, the first 4 bits correspond to the op, the second 4 bits correspond to R1, and the third correspond to R2, except in the case of ops 6, 7, and 8, where the first 4 is op, and the last 8 are the address. And that's all it's doing. You might also be asked in this class to actually figure out what R1 and R2 would be individually. Well, I mean, 32, that is this, I believe. Yeah, 1, 2, 4, 8, 16, 32. Yeah. So this is 32 and 8 as an 8-bit number. And so if we split this in half, so we have the two 4-bit numbers, this is 0 and this is 2. So really, you could say that R1 is 2 and R2 is 0, because if you sort of combine that and read that as a single 4-bit, or a single 8-bit number, it's 32. Also, if you could read this as hex, right? 2, 0, or 20 in hex is 32. So you get that. You could also put 2, 0 here. Generally, it's fine to just put 32, but if it specifically says to break it apart, or to give hex or binary values for every single R1 and R2, then you're going to need to break it down and put 2, 0. Just make sure you read carefully on whatever instructions. Any questions on this? All right. And then I'm going to do one last one, or maybe two small ones, and then I can take a look at some of the examples. So another couple of things to point out. These are the registers. All of these in this row here, these are the registers that you can put in for X and Y. Obviously not the X and Y, not the X's in instructions 6, 7, and 8, because those are supposed to be addresses. But anywhere else, pretty much, you see an X, that's supposed to be a register. And really, technically these are registers, but these are the general purpose registers. And these are the only ones that you can actually use in those instructions. If you need to use MAR or MBR, you have to use the specific instructions that are given to you to use MBR or MAR. Which also includes op15 over here, which is a little sneaky. Make sure you pay attention to op15 here, because it can be used to do something a lot faster. So let's see. I'm going to perform a read. So let me actually pull up the document really quickly of the problems, because I may just do one of those. Sorry about this. It's taken way longer than it should, because Google Drive isn't being cooperative. Okay, there we go. Yeah, so I'll go ahead and just look at that first instruction there. And then I'll also look at that second one, because yeah, that's where op15 comes in handy. So you have MAR equals PC, and then read. So here we can notice that if we do op 0, that's MAR equals PC, and then read is just op number 2. So we should be able to just do this and then this. I'm not going to write that out. So if we look at op R1 and R2, well, our first op is going to be op 0. And for MAR equals X, we put X as R1. So we want to put PC as R1. PC is register number 0, so we'll put a 0 here. And then R2, don't care what it is because it's going to get ignored anyways by definition of how the instruction is defined. So then we want to do the read, which is stop number 2, and we don't care what these are, right? Because the read is just an operation on its own. It's just going to perform that read and get the data, and that's it. That's the answer for number 1. Any questions on this? All right, so then there's number 2. So that's MAR equals PC, MBR equals AC. Right. So you might think here that would be op 0, then op 4, and then op 3, but that's wrong because op 15 does all 3 of those at the same time. It's just something that you have to note about these instructions here is that there is op 15. And the reason you can do that is specifically how you do this in the horizontal, where you send some of the data, like out through the B bus here, and the other data comes out through the ALU and up through here, right? Both of those can be set at the same time, and then you perform the write. So here this is just op 15. So we have op R1 and R2, and that's just 15. And then whatever we want to put into the MAR is X. So that's PC, whatever we want to put into the MAR is X, and we put X as R1, and so that's PC here, and we'll put that in R1, so that's register number 0. And then MBR is Y is R2, and so we'll put AC here in R2, which is register number 1. Any questions on that? Otherwise, that's pretty much it for vertical in terms of how that works out. So are there any last questions about the vertical architecture? Not about examples, but about conceptually what it is. So to answer the first question, the 32-bit thing again, what do you mean the 32-bit thing? Like the fact that these instructions here are 32 bits and these are 12? Oh, with op number 7. So okay, let me write this out. Yeah. So you have, really your instructions are a 12-bit number in the vertical architecture. So I'll mark this off as like the 12 bits for the instructions. And I'm not answering questions about examples right now, so I won't talk about that. But yeah, so for like op 7 here, what we do is an instruction is a 12-bit number. It doesn't have any parts. It's a single 12-bit number, and you could literally write every single instruction as just a number. I think it would be what? So that's 16. So 16,384. Any number between 0 and 16,384 is a valid instruction. It just specifies to the CPU what's going on. But really, that would be ridiculous, right? Imagine for this architecture, there just being a document with just a list of numbers, and for every single number, it tells you exactly what's going on. That would get a little bit ridiculous. So instead, we organize it a little bit more intelligently. So instead of just saying, okay, any arbitrary 12-bit number corresponds to some instruction, maybe like the instruction number 3 would correspond to adding 0 to TIR and putting it in SP, right? Or then the instruction 2 is you send AND to the MA, you send C to the MAR, right? You could do it in any arbitrary order, but that would be a massive burden to program. Instead, we say, okay, well, we're going to take the first 4 bits and we're going to call that op. And based off of this table here, you can figure out what the instruction is doing just based off of these first 4 bits. Well, now, in a lot of these instructions, what we're going to do is we're going to take the last 8 bits and we're going to split it up into R1 and R2. However, for instructions 6, 7, and 8, we're going to just take these last 8 bits, and this is just going to be our address here. And that's what this syntax means, right? It could have easily also been explained like this. And so in the first 4 is always the op, but the next 8 can either be R1 and R2 in 2 4-bit numbers, or it can be a single 8-bit number representing the address. Does that answer your question? All right, so the next question is, so for the conditional, you also need to remember to incorporate the LU for NZ, right? Every single time you have an if N or if Z go to, you absolutely have to do operation number 5 first. Otherwise, it just won't work or it won't work as expected. It'll do something based off of what the N and Z flags were set to, but really you want to set them to whatever you need them to. So you have to do this operation number 5 so the N and Z flags are set properly before you can do a go-to operation. Does that answer your question? All right. Anything else conceptually about the vertical architecture? Why the NZ instruction, you mean? As opposed to just how it's done in the horizontal? Or this NZ component here? So it's a little bit, okay, let's say you want to check to see if a number is positive, right? Obviously there's no if P go to X, right? And you can't do if N and Z go to, or like if not N and not Z go to something, right? There's no way to do that. With the horizontal, there's no way to do that either. Not in one instruction, at least. With the horizontal, you'd have to do something a little bit bizarre, right? You'd have to do something like ALU equals A, if N go to something, and then ALU equals A if N. With the vertical, the reasoning behind this is, let's say I have a value A, and I want to say if A is positive, do something specific. Well, what I can do is I can do ALU equals A NZ. Then what I can actually do, if I want, I can modify A. I can, set A to 5. I can do whatever I want to A, and the N and Z flags are going to stay the same. That's one thing that's useful about it, is you can sort of get the flags, do some other stuff, and then do a conditional on it. Like, let's say you're running out of registers and you need more room. What you can do is you can maybe check what that condition and then overwrite the value, and the condition, those N and Z flags are going to stay the same. They're not going to change unless you do this operation again. And so you can do that. But another thing is, what I can do is, let's say I wanted to do if positive, do something. Well, what I can essentially do is like, I have my register A, right? I'm going to set the N and Z flags according to A. Then if N go to, and I'm just going to draw an arrow here to be simple. I'm going to just jump over. Let's say right here is my code inside of the if. And just to write it out, what I'm trying to do here is essentially implement if A if A is greater than 0. Should probably write it there. If A is greater than 0, some stuff. Otherwise, just continue, right? And so what I'll do is I'll set the N and Z flags for A. If N, jump over the block of the if statement. If Z, go to the same place, right? So here, I set the N and Z flags once, and then I can check both if it's negative and if it's 0 in 2 different instructions, in the next 2 instructions. And if it's either negative or 0, I'll just jump over the code inside of the if statement. Otherwise, if it's positive, it'll go here, say, oh, it's not negative, so I'm not going to jump. Oh, it's not 0, so I'm not going to jump. And then it ends up inside of the if statement, executes the if statement, and then it finishes It just finishes by leaving the if statement. And so this is at least one way that you can do it. Yeah. Any other questions here? And I'll talk a little bit more about the lab after I do some examples, but all right.